Our first lesson in the forces unit is titled, What is Force? We have 3 learning targets for this video. You can see them here. The first of which we want to define force and give examples of forces. So defining force. A force is simply a push or a pull. We want to keep the definition nice and simple. Any sort of action that causes a push or a pull would be a force. The thing about forces is you experience them and use them every single day. So you are very familiar with them, whether you think you are or not. Your movement and your bodily functions depend heavily upon forces. Some examples of forces that you would certainly be familiar with. Gravity would be an example of a force. Friction is a force. Electric and magnetic forces. And then anything that you would consider to be a push or a pull. So simply you pushing your hand up against a doorknob to open a door, or you pulling a rope to pull a child in a sled. Those would be examples of forces. So we've looked at the first learning target here. We have given a definition for force and we've given examples of forces. Now what we want to do is we want to be able to define net force and relate that to balanced and unbalanced forces. So let's consider what happens if we're going to lift a really heavy box. So here's our box. If you're going to lift it, of course, you're going to apply a force in the upward direction. Now, maybe the box is too heavy for you to lift, perhaps. So what now? What do? Well, you're going to get a friend to help, of course. So you get your friend, and you have the box, and then if your friend's going to help you, your friend's also going to lift upwards like you did before. So now you have 2 forces pulling up on the box. Now I want you to consider what the consequence of this is, having 2 forces pulling up in the box. Well, what that's going to mean then is the total force acting on the box is simply going to be the sum, or the addition, of those 2 forces. This leads us to our definition of net force. The net force acting on an object is simply the total force acting on an object. So let's say if you and your friend each lift with 55 pounds of force, what is the net force acting on the box? So our scenario here is you're lifting up with 55 pounds, so is your friend. We want to know what the net force is acting on the box. Well, since they're in the same direction, I would just add them. The net force of 55 pounds plus 55 pounds is 110 pounds. And so we have 110 pounds for the net force. Now let's consider a different example. Let's consider a tug-of-war game. So here's our rope, and most of you are, I would guess, are familiar with the game of tug-of-war. If you're not, basically it just consists of a rope, and then there's a team at either end. A team at the left that would pull towards the left, a team at the right that would pull towards the right. And usually there's some sort of marker in the middle, like a flag or something, that once that flag crosses a pre-designated point on either side, then a winner is declared. So suppose Team A pulls to the left with a force of 250 newtons, and Team B pulls to the right with a force of 175 newtons. The question is, what is the net force acting on the rope? So here's a scenario. Team A is pulling to the left with 250 newtons. Team A is pulling to the right with a force of 175 newtons. Now a couple things I want to point out. First of all, the unit Newton. Yes, that is named after the physicist and mathematician Isaac Newton. It is the metric unit for force. This is a unit that we'll be very familiar with. We'll use it almost all the time when we talk about forces. The other thing I'd like to point out is how I have the forces labeled here. Notice the 250 Newton force I have labeled as positive, while the 175 Newton force I have labeled as negative. You might be wondering why that is. If you look at the statement here about the problem that 175 is not listed as negative, but I want you to consider this. These 2 forces are in opposite directions. So by definition then, one of them needs to be negative. Now it makes no difference which one you define as negative. I just as easily could have said the 250 was negative, so negative 250, and then a positive 175. Either way is fine, but by doing this, I'm showing that going to the left is we're considering positive, going to the right we're considering negative. And again, we could have flipped that around if we wanted to. So the question, what is the net force acting on the rope? Well, remember, net force is just the total force acting on an object. So I just need to add up these 2 forces. So that would be 250 newtons plus the negative 175 newtons. Notice here we're adding a negative, so you might remember from your math class it's the same thing as subtracting. So that gives us 75 newtons. And also notice that because we have defined directions with positive and negative, that this 75 newtons, because it's positive, we know that the net force is going to the left. This allows us here to look at what an unbalanced force is. An unbalanced force occurs whenever the net force acting on an object is not equal to zero. Notice the word not here. So anytime our net force is not equal to zero, so here we have a net force of 75 newtons, that would mean that the forces acting on this rope here are unbalanced. We could have said the same thing about the box in the previous example. Recall that that net force was 110 pounds, so that's not equal to zero, so the forces acting on that box were unbalanced. Let's look at a different example here. Let's consider a car moving down the highway. For this example, we will only consider the forces acting in the horizontal direction. If you don't recall what horizontal means, it means side to side, left to right, if you will. So here's our car, and the road here we can see, and the car is traveling. It looks like the car is pointed to our left here, because it looks like there's the headlights right there. So the car is going to the left. We're told 2,500 newtons of air resistance act on the car, while it is being pushed by 2,500 newtons of traction from the road. What is the net force acting on the car in the horizontal direction? So considering what we're told here, we're told 2,500 newtons of air resistance act on the car. Notice that the car we said is pointed to the left, so it's probably traveling to the left. So ask yourself, which direction would the air resistance be pushing the car? So air resistance, that's friction, so that would be going against the motion. So the air resistance would point to the right. So our air resistance is going to the right, and notice here I've labeled that negative 2,500 newtons. Like we talked about before, we could just as easily label that positive 2,500, that would be just fine. But for this example, I'll say going to the right is negative. And then we're told that the car is being pushed forward by 2,500 newtons of traction from the road. So that would be going to the left, because if it's going forward, then we said the car is going left. So that would be 2,500 newtons going to the left. And notice here that this is positive. If going to the right we've defined as negative, the force going to the left must be positive. So the question we're asked here, what is the net force acting on the car in the horizontal direction? Well, the net force, recall, is just the sum of the forces. So I'll add up 2,500 newtons plus a negative 2,500 newtons. And again, recall, adding a negative, that's just like subtracting. So 2,500 newtons minus 2,500 newtons, that is 0 newtons. We have a net force of 0. We would say that the forces acting on the car here in the horizontal direction are balanced, because a balanced force occurs whenever the net force acting on an object is equal to 0. So notice the net force here we have calculated as equal to 0. So the forces acting on the car here, at least in the horizontal direction, are in fact balanced. So let's summarize what we've learned here about net force. We've said that net force is simply the total force acting on an object. An unbalanced force, this is whenever the net force is not equal to 0. While a balanced force, that is when the net force is equal to 0. Going back to our learning targets here, we have now defined net force and we've related that to balanced and unbalanced forces. Our last learning target for this video. We want to be able to explain how the force acting on an object affects its motion. So let's consider that tug-of-war example from before. So here is our rope, and we were told that Team A pulled to the left with 250 newtons, and Team A pulled to the right with 175 newtons. And again, recall we defined going left as positive, so this was a positive 250 and a negative 175 newtons. So suppose the rope starts from rest. So maybe we're looking at this situation as soon as this tug-of-war game begins. So perhaps a whistle is blown and both teams start pulling, so that rope is starting from rest. The question we're asking here, will the rope stay at rest if these forces act on it? So we're talking about these forces we have labeled up here. Recall that we calculated the net force, and we said the net force was 250 newtons plus a negative 175 newtons, which gave us 75 newtons for the net force. And do notice here I have that labeled left. I know that's left because was a positive 75 newtons for the net force, and we said positive was going to the left. So here's the deal. Simply answer the question. The rope will not stay at rest. It will start moving to the left. And I think intuitively, most of you would probably understand this. The net force here is pulling it to the left. So if the rope is starting from rest and there's a net force pulling it left, it will start to move to the left. So no, the rope will not stay at rest. Now consider this situation. We said that it started moving. So it wasn't moving to start with, and then it was moving. Well, this means that the rope is accelerating because it's going from zero velocity to some non-zero velocity. So it is, in fact, accelerating. So this leads us to our next question. If these forces continue to act on the rope, so if these two forces that I have labeled up here, if they don't change, will the rope continue to accelerate? So will it continue not just to move to the left, but to accelerate to the left? And the answer is yes. As long as the net force acting on the rope is unbalanced, it will continue to accelerate. In other words, if we were watching this tug-of-war game and these forces were constant, so the team on the left pulled to the left with 250 newtons, the team on the right pulled to the right with 175 newtons, the rope would start moving to the left and it would actually speed up the whole time to the left as long as these forces here remain constant. And again, that is because the forces acting on the rope are in fact unbalanced, so it will continue to accelerate. So in summary, this whole slide here, if we want to summarize it, what we can simply say is this. Unbalanced forces cause acceleration. If you're going to remember one thing from this slide, that would be it right there. Unbalanced forces cause acceleration. So let's consider the car example from before that we looked at. And just a reminder here, we had a car that we said it was traveling to the left, and the traction pushing the car to the left was 2,500 newtons. The air resistance pushing the car to the right was negative 2,500 newtons, just because it's opposite of the traction. All right, so here's our question. Suppose the car is traveling to the left at 25 meters per second. Will the car speed up, slow down, or continue at the same velocity with these forces acting on it? And again, consider our net force calculation that we did before. We did 2,500 newtons plus the negative 2,500 newtons, so our net force was 0. And recall that we said that meant that the forces acting on the car were balanced. Anytime the net force is 0, that means there are balanced forces. So what do you think? Will the car speed up, will it slow down, or continue at the same velocity? Pause the video and think about that for a second. So you've had a chance to think about this. I'm guessing that some of you said that the car will slow down and then eventually stop, thinking, well, if the net force is 0, then how can the car be moving? So it would have to stop. Well, actually, that thinking, while it is very common to think that way, is actually incorrect. Note here that we said that the forces acting on the car are balanced. Now let's think about what that would mean for motion. Well, considering what we learned on the last slide about unbalanced forces, recall that we said unbalanced forces cause acceleration. So considering that means that balanced forces cause no acceleration. No acceleration if we have balanced forces. Now, no acceleration, that just means we're going to have constant velocity. So, to answer the question, the car will continue to travel at constant velocity due to the presence of balanced forces acting on it. That is exactly what balanced forces do. They cause no change in velocity. There's no acceleration, so we have constant velocity. So, in summary, balanced forces cause objects to have constant velocity. In this case, that constant velocity is the 25 meters per second going to the left. Ask yourself this. What if the car was at rest, if it wasn't moving, and these forces acted on the car? What would that mean? So you've had a chance to think about it. The fact that it's not moving doesn't change the fact that the forces are balanced, meaning it will have constant velocity. In this case, if the car is not moving to start with, it will continue to not move. It will have a constant velocity of 0 meters per second. So it would just sit there. It wouldn't go anywhere. Alright, so we have looked at all three of the learning targets. The last one here, we've explained how the force acting on an object affects its motion. There's a few slides here yet that I want you to look at and watch the video here. There's just some review and practice questions. For each one, once you see the question, pause the video, think about it, answer it yourself, perhaps even write out the answer or try to work the problem, and then play the video to see if you got it right. Alright, so review and practice questions. First question, what is a force? So pause the video and see if you can answer that question. So you've had a chance to think about this question, and a force, if you recall from the very first part of the lesson, is simply a force is any push or pull. That's all a force is. Any push, any pull, that is a force. Okay, second question. What is a net force, and how is it calculated? So a net force, the net force acting on an object is simply the total amount of force acting on it. To calculate a net force, simply add all of the forces acting on an object in a particular direction, meaning vertical or horizontal. And those are all the examples that you saw in this video here. As we go through this, we'll have more complex scenarios, but we can always break it down into vertical forces. Remember, vertical would be up and down, horizontal would be left to right. And then remember that when we add these, be sure to account for the fact that some forces are in opposite directions. Recall in most of the examples that you saw here in this video, we had forces that were positive and forces that were negative, where the positive and negative are just indications of the direction. Alright, next question. Determine the net force acting on the following skydiver. So here's our skydiver. Notice we're given some forces here that are acting on the skydiver, and we're asked what direction is the net force in. So pause the video, see if you can figure this out. Alright, you've had a chance to work this, and you'll notice there are two forces acting on the skydiver. Air resistance pushing the skydiver up, which we're told is 350 newtons, and then weight, or that's simply the force of gravity, pulling the skydiver down with a force of 600 newtons. And notice here that in this problem we've defined up as being positive, so positive 350 newtons, down would be negative then, so negative 600 newtons for the weight. So to find the net force, we simply add the forces together, so 350 newtons plus a negative 600 newtons, so 350 minus 600, that is negative 250 newtons. And then the second part of the question here asks what direction is the net force in? Well, the fact that the net force is negative tells us that it's down, because that's the direction that we define as being negative up here in the problem that was given to us. So the net force acting on the skydiver is 250 newtons in the downward direction. Next question, still related to the skydiver. Are the forces acting on the skydiver balanced or unbalanced? How do you know? Will the diver be falling with constant velocity? How do you know? And if you didn't remember, here are the same data that we saw on the last slide. So the first question there, are the forces acting on the diver balanced or unbalanced? Well, here's what we can say. The forces acting on the skydiver are unbalanced. And we know this because the net force acting on the skydiver is not equal to 0. Recall the net force calculation from the previous slide. We calculated the net force to be 250 newtons in the downward direction. So it's not 0, so the forces are in fact unbalanced. Next question, will the diver be falling with constant velocity, and how do we know? Well, the diver will not be falling with constant velocity, and we know this because unbalanced forces cause acceleration. The forces acting on the skydiver are unbalanced. We identified that in the previous answer, and so those unbalanced forces cause acceleration. So the diver will be accelerating in the downward direction because the net force is in the downward direction. We can see that because the weight of the skydiver is greater than the air resistance acting on the skydiver. This is the last review and practice question here. We're told a car travels down the interstate at a constant 65 miles per hour. 30,000 newtons of air resistance act on the car. There are two questions. Question A, are the forces acting on the car balanced or unbalanced? How do you know? And question B, how much traction must be pushing the car forward? So pause the video, see if you can answer this. Now I would recommend that you try to draw some sort of diagram just like you've seen on all of the previous problems. Alright, so you've had a chance to work this and you've tried to draw a diagram hopefully. Here's a diagram that I might draw. So here's our car, and notice here in this case the car looks like it's pointed towards the right. So we'll say that the 65 miles per hour that we're told that the car is traveling down the interstate at constant 65 miles per hour, that would be to the right. and we're told that 30,000 newtons of air resistance act on the car. Well, if the car is traveling to the right, the air resistance would be pushing against it, so that 30,000 newtons of air resistance would be going left. And notice here I have labeled that a negative 30,000 newtons. You could label that positive 30,000. There would not be anything against that. The one thing I would say, though, is if we're calling this a positive 65 miles per hour going to the right, then going to the left, by definition, then must be negative. So that's why I chose to label that a negative 30,000 newtons. All right, first question. Are the forces acting on the car balanced or unbalanced? How do you know? Well, at first thought, you might be thinking one of two things. Either A, we're not given enough information because we don't know about this force here going to the right, even if there is any. Or B, you might say, well, it has to be unbalanced because there isn't a force going to the right. All we see here is this air resistance going to the left, so they must be unbalanced. But consider this. If we look back at the initial statement, we're told that the car travels down the interstate at a constant 65 miles per hour. So if the car has constant velocity, what does that mean about its acceleration? Well, constant velocity means no acceleration. So note that we are being told the car is traveling with constant velocity. This means the forces acting on the car must be balanced. Balanced forces means no acceleration. The car will have constant velocity. So we've answered the first question. The forces must be balanced. And again, we know that because of the constant velocity of the car. Second question. How much traction must be pushing the car forward? Well, if we consider our answer to the first question, we know that the forces are balanced, and that means the net force has to be zero. Since the forces acting on the car are balanced, the net force acting on the car must be zero. So think about how much force we have to be pushing this car forward, the traction, in order to have a net force of zero, considering how much we know the air resistance is. Thinking about that, the answer is 30,000 newtons. Thus, there must be 30,000 newtons of traction pushing the car forward to balance the air resistance. So if I draw a diagram there, add to my diagram, here's 30,000 newtons of traction pushing the car forward. 30,000 newtons plus a negative 30,000 newtons, that would equal zero for the net force, and that's exactly what we said it had to be. So this concludes the first lesson on forces. We've looked at how we define force and net force, looked at balanced and unbalanced forces, and then how those forces, balanced and unbalanced, relate to an object's motion, meaning whether it will accelerate or whether it will travel at constant velocity.